All right, so in this first lecture, we're going to start the study of magnetic circuits. And this is an essential foundation for any electric machine. As you probably know, an electric machine is an actuator that will convert electrical energy into mechanical energy. And that process passes through a magnetic energy conversion. So we go from electrical to magnetic energy to mechanical energy. And the interaction between them is what creates this transducer, what makes most of electric machines work. So a solid understanding of magnetic circuit is very important. And you need to start here, create a basis, and then go on. You have seen most of these topics in physics, so I'm going to go over them not in great details. I'm going to condense everything in this lecture, and then in the next lecture, we're going to use some of the concepts to develop transformers. So today you're going to look at the relation, for example, between current and magnetic field, understand the concepts of electromagnetic induction and the differences between, say, magnetic induction, magnetic flux density, and the magnetic field itself, and model a simple electromagnetic circuit that will later be used to develop more complex electric machines. So again, for any electric machine, we'll see that there is some use of magnetism there, and we need to study this in detail before we go on and before we are able to model these machines in detail. Other than electric machines, we see applications of magnetism everywhere. A very simple one that you can think of is a MRI system. We could ask the question, how much energy is required to create, say, a 2-3 Tesla into a into cylinder that has a radius of 1 meter, for example. It takes quite a lot of energy. The circuitry behind it is quite complex. In addition, how can we orient the magnetic field so that we always get an exact cross-section on the image? This is the example I was talking about. We have electromagnets or any sort of mechanism that any sort of actuators will be based on some sort of energy conversion from electrical to mechanical, and that conversion will pass through the magnetic portion. Here we have a very simple actuator. This is an electromagnet. You know how this works. You have a coil around the ferromagnetic core. And once you turn the coil on, we pass a current through the coil that creates a magnetic field, and the magnetic field attracts these plates together. A very simple actuator. How can we model and design this electromagnet? How much current does it take to create a force? What is that relation? Right, this is a very elementary electric machine, but is exactly how more complex ones will work later. Other applications include, for example, induction heaters, or even induction stoves at home. We pass a current through a coil. That current creates an alternating magnetic field. And when you expose a conductive material that is also electromagnetic, that it creates current in the material itself. And those currents, because of Joule losses, will convert that energy into heat. And that's the principle of induction stoves and the principle of any induction heaters. All right, so let's get started with the basics of it. So the first thing we need to know is very simple, is that a steady current creates a steady magnetic field. So let me repeat that. A steady current creates a steady magnetic field. And that is given by Unpaired Circuit Law. If you have a conductor that we see here that carries a current I, that current, even if it's DC, will create a constant magnetic field. And the magnetic field that we have here called H is the notation for the strength of that magnetic field. We have this conductor carrying the current that creates a magnetic field, and you can now see in which direction that magnetic field rotates by simply using your right hand. So put your thumb towards the current and curl your fingers around the conductor or around the current itself. So in this particular case here, the magnetic field rotates counterclockwise. See, the current goes that way, and then my fingers will give the direction of rotation of the magnetic field. Unpaired circuit law is very simple. It states that if you take a closed surface and we count, and you look at how the currents coming in and out of that surface, we can relate them to the intensity of the magnetic field. And that is given by the first equation here. Integral of HDL gives the current. So integral of HDL equals to the current. H is the intensity of the magnetic field, and dl is a differential element of that closed path. So let's look at this example here. We have a magnetic field that is created by these three currents, I1, I2, and I3, and you're going to define a closed path. Notice that the integral is given in a closed path. The little circle there is not there just because it's nice. It indicates that this surface that we are going to take the integral of must be closed, must be a closed surface or a closed path. Let's put it that way, it's better, a closed path. dl then is a differential element along that closed path, okay? And this gives all the current passing through that surface contained by that circle. So the integral of HDL, we see also that this has a dot here that indicates the cross product, which also indicates that we are looking at the current that passes through the surface that is perpendicular to the surface. All right? So if the magnetic field and the current now have an angle of theta that is accounted for in that dot product. If H and I are perpendicular, then nothing is passing through the surface and we have a dot product that's zero. In this particular example now, if you go along the surface and you take the integral of HDL, that will give us the net current flowing within that circle. That's what you see here. We have three currents, I1, I2, and I3. I1 and I2 are going upwards and I3 is going downwards. So they will, one of them will cancel out, or you have to subtract I3 from the other two. And the result is the net current through that surface. Okay, and this is the Ampere's circuit law. In other words, we can read this circuit law or this equation as a steady current creates a steady magnetic field. Okay, any questions so far?
I have one question, Dr. Rosa.
Yeah, go ahead.
Or actually a couple questions. So my first question is, just to clarify, the currents that is found within our closed surface, they have to be perpendicular to the surface, I guess?
No, they do not need to be perpendicular. The integral will take care of that because of the dot product. We are considering only the projection of the current that is perpendicular to it, right? It's basically the angle between H and I, but that is already accounted for in the dot product. If they happen to be orthogonal, then the result is zero.
Okay, and then my other question is, what's the relevance of our, like, changing the enclosure? Like, if I had an enclosure that only captured I1 and I2 in this case, what does that represent in terms of the magnetic field? Is it talking about the magnetic field produced by I1 and I2, or?
Yes, that is the net magnetic field produced by all currents, right? By all currents. If you only enclose I1 and I2, your magnetic field will be greater than if you enclosed all three. Right? It's the net magnetic field generated by all those currents.
And in the physical capacity, you would be observing in real life an enclosure of all three currents. Like, is it possible to observe an enclosure of only two currents with another current nearby?
Oh, that's a good question. It really depends on how you define your surface. If you have the physical capacity to do that, then yes. But in most cases, no, because you don't have control of which currents are going through your surface. You may have currents that are coming from the current itself, the source, but you may also have currents that are induced by that own current and that will oppose the magnetic field. So it completely depends on your physical capacity to do that.
Okay,
Okay.
so I guess for the most part for this course, we're going to be assuming that all currents are enclosed in our
Yes,
in
yes,
a
as you're
surface.
going
Okay.
to see in this slide here. So for
Okay.
that, let's consider this example here. Have this ferromagnetic path. Let's assume that this square is a ferromagnetic path, and you have now a coil around it, and that coil has n turns. Now let's do the integral of HDL. Let's apply Ampere's law. And now let's define this as our line, as DL, as the path. When you take now the integral of HDL, what should it give? So DL now is constant, so that becomes L, H times L. And we have a current I through a coil. So if we only had one turn, that would be equal to I. But now we have how many times the current going through that surface? N times. So now the result of this is N times I. We have the current going through the surface N times because of the coil that goes through that N times, okay? And this is what we call, this Ni is what we call the magnetomotive force, is what drives a magnetic flux or a magnetic induction in a circuit. Now, in the same way, a voltage drives a current through an electrical circuit, the magnetomotive force drives a magnetic flux through a magnetic circuit, okay? All right, so we established that a steady current creates a steady magnetic field. Now I have a question. Does a steady magnetic field create a current? Any guesses?
No.
Does a steady magnetic field create a current? No, if it did, then all we would have to do to create energy was to approach a magnet to a wire, hold them steady, and a current would flow through that wire. So that doesn't work. And Faraday was investigating this, and he immediately observed that, well, that cannot happen. There would be free energy. And here is the setup that he built. This setup has two coils. They have a first coil right there. Let's call this coil 1. And this coil is connected to a battery and has that switch. When you close the switch, the current flows through the coil, and that establishes a magnetic field that we see from these dashed lines. He then built another coil and exposed that coil to the same magnetic field generated by the first coil. Let's call this one coil number 2. And let's put here a amp meter or a multimeter, doesn't matter. You notice something interesting. When we close the switch and establish a field in coil 1, coil 2 has no current. And that's not surprising because a steady magnetic field does not create a current, but a steady current creates a magnetic field. And when he opened the switch, of course, there is no magnetic induction on the first coil. There is nothing showing on the second coil. But he noticed that as he was opening and closing the switch, a current would appear in the second coil. And therefore, he concluded that the induction in the secondary coil depends on the changes in the magnetic field from the first coil, not on the intensity of the magnetic field, but on the changing magnetic field in the first coil. And the conclusion is now a changing magnetic field will create a changing current in a conductor that is exposed to that same magnetic field. Right? And this is what we call in control systems the electromotive force, or the EMF in a DC motor. That's exactly what it is. All right. So now I have two concepts. We have the electromotive force. This is what drives a current in an electrical circuit, is a result of a conductor being exposed to a changing magnetic field. And we have the magnetomotive force, which drives a magnetic flux through a magnetic circuit. This is our NI from before. All right, so these are two different concepts. Are we good so far? All right, so Faraday's law states that a changing magnetic field creates a current in a conductor that is exposed to that changing magnetic field. Ampere's law says that a steady current creates a steady magnetic field. Now we can take this approach one step further, and the idea is very simple. Now I'm going to have this wire is a closed path, and I'm going to approach a magnet to this wire. This magnet, say the magnet is moving downwards. So the magnet is moving downwards, and let's assume that the magnetic field it produces is pointing down, is increasing downwards. Because now the magnetic field from the wire's perspective changes, a current is induced in that wire. That current, in turn, will create a magnetic field itself. And here is the catch. That magnetic field created by the current needs to oppose the magnetic field from the magnet. Now that's Lenz's law. The current created or induced current in this wire will oppose any further changes of the magnetic flux or the magnetic field. Right? And that's very unfortunate, because otherwise we would have free energy. We approach a magnet, and then if the wire would attract the magnet, we would basically have free energy. But it turns out that the magnet will create a force, sorry, the current will create a force that opposes the magnet. And this gives us in which direction the current must flow. So again, if the magnet here is going down with a flux B, then it's going downwards, and the wire needs to create a current that will oppose B. So the current now needs to create a magnetic field that goes upwards. Let's call this B current. So the magnetic field created by the current needs to go up, which means that the current now flows in a counterclockwise direction. And that's this negative sign in Faraday's law. So we saw that the induced electromotive force depends on the changing magnetic field. And then Faraday's law states then the induced EMF is simply the derivative of the magnetic field over time. Lenz's law adds this annoying negative sign in front of it. And this little negative sign there has a lot of implications, because it tells us exactly in which direction the induced current must flow to oppose changes of the generating magnetic field. All right. If now this wire has, let's say, a resistance of R, then the current is very simple to calculate, is the induced EMF divided by the resistance of the wire itself. Okay. Any questions here? No? All right, this is a simple concept. And what you take from equation 3 is, again, that you see it's the derivative of phi with respect to time. So if phi is constant, that's 0. There is no current induced. If now phi changes over time, the magnetic flux changes over time, then there is an induced EMF. That induced EMF creates a current in a closed loop circuit. That current creates in turn its own magnetic field. And because of this negative sign in Faraday's law, then this magnetic field opposes further changes of the originating magnetic field, the original magnetic field. Right? And you see here that we have d phi dt. Phi is the magnetic flux they're going to define later. It's basically what is analog to a current in the electrical circuit. Now let's take the same example, but now add more wires. Now we have a solenoid in the same way that we had for that one in the second slide. Now instead of just having one wire, we have n wires. So if we have n wires, then we have n wires being exposed to the same magnetic field. And you see that this is one in the same direction. So now to find the electromotive force, we simply multiply everything by n, by the number of turns in that coil. Okay. This wire, because of the negative sign, we will, the magnet, because of the negative sign, will experience a force pushing it back up. Right. So when you approach the magnet and a current is established, we'll see later that this magnet will be subjected to a force in the opposite direction because of this reaction from Lenz's law, from this little negative sign here. So for one wire, the electromotive force is d phi dt. For n wires in the same direction, of course, that is that times n. If half of the wires are in one direction and the other half are in the other direction, then the net EMF is 0. Right? Current flows for half of it in one direction, for half of it in the other direction, and the result is 0. Okay, so let me give you an example here. I think by now we have a fairly good idea of how this works, of how induction works. But let me ruin that understanding for you with a simple example. Where is my example? Here it is. All right, let's assume that I have a circuit. Where is my example? Just give me 1 second. Here it is. Let's assume that I have a circuit like this. I have here a resistance of 100 ohms. I have here a battery of 1 volt. And here I have a battery of, a resistance of 900 ohms. Let me call this point here D, and this point here A. What is the current flowing through this circuit? Any guesses? What is the current flowing here? The current is simply V over these two resistors, 100 plus 900. This is 1 volt, so the current will be 1 milliamp. Okay, 1 milliamp. If the current is 1 milliamp, what is the voltage across this resistor? So the voltage across that resistor is 100 times 900, 1 milliamps times 900 ohms, that is 0.9 volts. Because this circuit is in parallel, right? So the voltage drop on this side is also 0.9 volts. And this is easy to calculate. We can take simply 1 volt minus the voltage drop here, 100 times 1 milliamp. And this gives exactly the same thing, 0.9 volts. Nothing surprising here because the circuit is in parallel. If I measure the voltage on this side or on that side, everything is the same, is 0.9 volts. Now let's do something different. Let's take this battery away. Let's remove the battery. And let's replace the battery with something a bit more interesting. Let's get rid of the battery and let's make a magnetic field pass through this circuit. And let's assume that this magnetic field that is coming out of or coming towards me is increasing and is creating a EMF of exactly 1 volt at 1 instant in time. Interesting coincidence. So there is a magnetic field coming out here. It's increasing. So d phi dt is not 0. That creates a magnetic induction. That creates a current through here. And that current and that voltage is 1 volt. Right? 1 volt. So what is the current through the system again? Well, if this is the same voltage we had here, at 1 volt for the battery case, the current is again 1 milliamp. The current is again 1 milliamp. Now, what is the voltage drop here? The voltage drop there is the same, 1 milliamp times 900, that is 0.9 volts. Nothing crazy here. What is the voltage drop on this side now? The voltage drop on this side is 100 times 1 milliamp, that is 0.1 volts. That is 0.1 volts. So physically, if you take a multimeter and we measure the system from this side, from DA, we have 0.9 volts. If you measure the system from the other side, we have 0.1 volts. What is this? This doesn't make any sense. These two things are in parallel. They should read the same voltage. Kirchhoff's law states that if we do a closed loop, we must have 0. So why is this not the same? If you do here a closed loop and we sum all the voltages, what do you have? 0.9 plus 0.1, 1 volt. It should be 0 according to Kirchhoff's law. And this thing turns out to be 1 volt. So what the hell is going on here? Sorry for the language, but this is indeed interesting. And I get overexcited. Is the magnetic field. Kirchhoff's law could be stated by saying that the integral of the electrical field dl equals to 0. The sum of all voltages is 0. But there is a magnetic field here, my friends. And this magnetic field is the result of this integration, d phi dt. So Kirchhoff's law breaks down. It doesn't work. It doesn't work because you have a magnetic field in here, and this magnetic field is non-conservative. The magnetic field is non-conservative, which means that a Kirchhoff's law does not hold. If we didn't have a magnetic field, then this part of the equation here is 0. And then you go to integral of EDL equals to 0, which is Kirchhoff's law. But notice that a Kirchhoff's law is a special case of Faraday's law. Here we have Faraday's law, right? The sum of all voltages equals to d phi dt. And this is phi, changing, right? So Faraday's law always holds. Kirchhoff's law is a special case of Faraday's law and only holds in the case of a conservative magnetic field. And in this case, the magnetic field is growing that way. It's non-conservative. The gradient of the magnetic field is non-zero. Right. So we talked about the flux density. Any questions about that?
Hi, I just had a quick question.
Yeah, go ahead.
In that, like the voltage in both cases was being measured at points A and D, like from both sides, like it's being measured at points A and D.
Yes.
Can they be different when they're being measured in the same?
It would be different. Yeah, because you see, this is very non-intuitive. Because now, and this is a good question. It doesn't make any sense, but it turns out because you have a non-conservative magnetic field, if you do this integration from A to D, EDL, this is not the same anymore as the integral from A to D, EDL. The work done by the particles that have to travel here, by the charges, now depend on the path they take. In a conservative magnetic field, that doesn't matter. If you go from A to D, from D to A, it's fine. Think about lifting a mass, for example. It doesn't matter which path we take, the potential energy of that mass will only depend on the initial and the final point, not on the path it takes. But that only holds when you have a conservative field of forces. When the field is not conservative, the work done by the mass depends on the path. So now it's the same here. We have a non-conservative magnetic field. And now if you go from A to D, that is not the same as going from D to A. The path now matters. And physically, you can actually do this experiment and see if you can recreate this, that this will differ. If you put your multimeter on one side and on the other side, the measurements will be different. There are some demonstrations online. I can send you the link to that. It is very non-intuitive. It is very, very complicated to grasp.
Thank you.
But that's what it is. All right. Okay, so let's go back here. I need to define some other things. The first concept is the magnetic flux density. And that is called B. The magnetic flux density is basically the number, generally speaking, the number of magnetic flux lines passing through a surface. In this, for example, we can think about a current density in a wire. You take a current, how many current lines are passing through that wire. We divide that by the area, that gives the current density. Here's the same. We have a magnetic flux density, which is the number of magnetic lines of flux that pass through a surface. And this is given here. We can relate now the magnetic field intensity, H, with the flux density to that constant mu. Mu is the permeability of the medium, the same as a resistance in an electrical circuit. The permeability of the medium is can often be expressed in terms of the relative permeability of the vacuum. So mu equals to mu r, mu zero. Each ferromagnetic material, or even no magnetic material, has its own permeability. We can do the absolute permeability. So when you refer to mu, it's the absolute permeability that has its own unit. Or we can say the magnetic permeability depends on, is relative to the permeability of the vacuum. Let's say, for example, we say that iron has a relative magnetic permeability of 1000. When you say relative, we say relative to the vacuum. So mu r would be for iron would be 10,000. I think I lost connection here. First incident.
No, sir, you're good, it seems.
Just one second.
Yeah, it seems you're okay.
No, I definitely did. I wrote some stuff here and it's not showing up. This is work in progress. We'll get. Okay, now it's fine. All right, there we go. Okay. So you understand the differences between them. So mu zero is the absolute permeability of the vacuum, that is 4 pi times 10 to the power of -7. And mu r is the relative permeability of the medium. It doesn't have a unit, it's just relative to mu zero. Right? And the unit for the magnetic flux density is Tesla, the famous Tesla unit, or Weber per meter square meter, or also Gauss, that is one Tesla equals to 10,000 Gauss. Okay, in your picture, this picture is not showing very well here, but you can see that in your copy there. You see that for areas in this circuit where the cross-section is smaller, we are passing the same amount of flux, so the magnetic flux density must be higher in areas where the cross-section is small. Okay, so this is now the relation between the magnetic flux density and the strength of the magnetic field. This constant is the permeability of the medium, or the equivalent to the resistance in the electrical circuit. Now let's define what the magnetic flux is. If the magnetic flux density is how many lines pass through a given area, then the magnetic flux itself is how many lines we have of induction passing through a surface. So if B is our magnetic flux density, and when you talk about flux density, we need to define an area. Now, if you multiply the flux density by the area, we get the magnetic flux phi. All right, so let's say this area that we have in the first figure here, we have the vector that defines this area is dA. And you have magnetic flux density B going either upwards or on an angle. To find the total magnetic flux, which would be, again, equivalent to the current in an electrical circuit, we simply take the integral of them, again, with a dot product here, because we are interested in the number of magnetic flux lines that are perpendicular to that surface, hence the dot product. Hence the dot product. If we have a constant area, then phi equals to BA. And here we have a better explanation for the definition of B. B equals to the magnetic flux divided by A. And B is the magnetic flux density. That makes perfect sense. It's a bit clear on this approach, on this equation. We know that the magnetomotive force is defined as d phi dt. So we now can take our magnetic flux and include that in this definition. Right? And you can now calculate the total induced EMF based on two interesting things. instead of the magnetic flux or variations of the magnetic flux, if we define an area through which that magnetic flux is passing through, then you can see that the induced EMF now depends also on the area, is the derivative of the integral of BA. I remember that a BA is simply phi for a constant area. This goes back to equation 9. So now depending on the size of our circuit, the intensity of the magnetic field, both of these quantities will define the amount of induced EMF. Okay. All right, so now let's go back here. For a closed surface that is subjected to a magnetic field density B, we can find the magnetic flux as the integral of B dA. Again, if A is constant, is known, then the magnetic flux is simply the magnetic flux density times A. What is B? B can be now related to the material properties of that surface and can be related to the magnetic flux density. Sorry, to the intensity of the magnetic field. So B, we can write B as mu H. Mu is the permeability, H is the intensity of the magnetic field. What is H? H is the intensity of the magnetic field that you can now relate to the current that originated that. So H integral of H dl equals to Ni, assuming that a dl is known, so HL equals to Ni. And H equals to Ni over L. If you now combine all these equations we get here, so first replacing B with mu H, now we replace H with Ni over L. And now we just move mu A downstairs, and we end up with this expression here. So the magnetic flux depends on Ni divided by L divided by U times A. L is the length of that path, the length of the path it goes through. Mu is the permeability of that medium, and A is the cross-sectional area. This entire section here, Al divided by mu times A, is what we call the magnetic reluctance. Is the equivalent to the electrical resistivity in a electrical circuit. This represents how easy it is to establish a magnetic flux when a current I is applied to the system. The magnetic reluctance is an indication of how hard it is to establish a magnetic field in a given material for a given current and a given number of turns. So once again, A would be the area of that surface, and L would be the length traveled by the magnetic flux lines. Okay, and R is then the magnetic reluctance. We can now define the magnetic flux as N times I divided by the reluctance. Ni are let's say that the input to the system. R depends on the properties, the electromagnetic properties of the material itself. We can now make here an analogy to an electrical circuit. In an electrical circuit, what is the driving force to a current? That is the voltage. We apply a voltage to a system, we develop a current. The system has a impedance, in this case here, just a resistance, R. And that is a simple electrical circuit. If you're now looking at a magnetic circuit, then our driving force now becomes Ni, the magnetomotive force. The resistance is the reluctance, and the magnetic flux is the current. So this is the analogy that you have between them. So let's do this I equals to V over R. And we see the analogy in a magnetic circuit, phi equals to Ni over R. Current is analog to the flux, voltage is analog to the magnetomotive force, resistance is analog to the reluctance. The resistance would be calculated by looking at a cross-section of a wire, the length of that wire, and this area, wouldn't it? And the reluctance is the same. And of course, the permeability or permittivity or conductivity of that wire. In the same way, the magnetic reluctance is defined as a function of the dimensions of the conductor and on the characteristics of the material itself, in this case, mu, the permeability of that magnetic material. So here we have the definition again. L is this length traveled by the magnetic flux, mu is the property of the material, and A is the cross-sectional area through which that passes. Okay, any questions? Now, I think this analogy is relatively easy to understand. The same way you calculate things in an electrical circuit, but here we have different variables and different properties. So if there are no other questions, we'll move on. One thing that I forgot to mention earlier is that the relative permeability of air is 1, or for any non-magnetic material, like plastic or anything that is not ferromagnetic, then the relative permeability is 1, which means that they have the same permeability as the vacuum. Right? It is very hard to establish a magnetic field in them. The higher the higher the permeability, the easier it is to establish a magnetic field. So iron, for example, would have a relative permeability of around 10 to 50,000, whereas air, the relative permeability is 1. It takes, put it that way, it would take 10,000 times less in magnetomotive force to establish the same magnetic field in iron than it would take in the air. There are many applications of this phenomenon. Here is one. Foucault currents are very common. Foucault currents or eddy currents are the currents that are generated through this induction process. We have 2 ways to create that. Let's consider the first case. We have a ferromagnetic plate that moves at a speed v. And we have now a magnet that creates a magnetic field. As this plate moves, locally, parts of the plate will be exposed to a changing magnetic field, right? As the plate passes under the magnet. That results in a changing magnetic field, and that must result in a current because of Lenz's law. And that current, if we have a conductor, will be established. The current will create an induction itself. That will oppose changes in the first magnetic field. But that current now dissipates energy in the form of Joule losses. Right? And you can have this to operate in 2 ways. The first one is like a brake, for example, in a high-speed trains operate on this principle. The plate, as it passes under the magnet, is subjected to these currents. These currents create a magnetic field that opposes the first magnetic field, and they will be opposed. So there will be a resistance to move that created when you move the plate under the magnet, and that resistance will increase the faster you go. The other application is heaters. Now you can have now a changing magnetic field. There is still a force between them, but there will be a lot of energy dissipation because this current will create heat in the form of Joule losses. The second picture here shows how brakes are actually, eddy current brakes operate. We have now a plate that rotates under that magnet, and the faster we go, the higher the resistive torque it takes to make that turn. Right? That's exactly how some, at least the early versions of high-speed trains used to operate. That's the sort of brakes we had there.
And someone asked if you could go over eddy currents again.
Yes, eddy currents?
Yes.
Yes, so just give me 1 second, I'll finish the light board. And this is the worst part of a light board, is that it needs to be cleaned. All right, so let me go back here. All right, so the eddy current is a direct result of Faraday's law. When you have a changing magnetic field, we noticed Faraday's law is stated that in a changing magnetic field, a conductor will be subjected to a EMF. Is that concept clear? All right, that's the first step to understand the eddy current. So if you put a conductor in a changing magnetic field, there will be an EMF. And if that conductor is closed, then the EMF is like a voltage and will create a current in that conductor. Here we have something very similar, but instead of a conductor, we have a plate. The plate is actually a conductor. And these little lines that we see there, we can see them as wires, in closed loop wires that are in that plate. So there is no difference from this to the first example that we saw, where you had a wire and a magnet going up and down that will create a current. Here is the same. These currents will actually be created in the material itself, within the material. They will find their own closed path and will establish there. Right? So there is basically no difference compared to the first example. It's just that here, instead of a wire, we have a material. If the material is conductive and is ferromagnetic, then eddy currents will establish. These eddy currents create their own magnetic field, and this magnetic field from these currents oppose further changes in the originating magnetic field. They oppose further changes in the originating magnetic field. That is Lenz's law. That is that a negative sign in d phi dt. Because of that, then these two plates will be subjected to a force that will try to move them apart. And that's how a brake works. Because of that force, if you move the plate under the magnet, you will experience a force that is in the opposite direction as the velocity. In a induction range, for example, this is the same principle. Your conductor is the pan. The pan under it has, under the pan, you see there is a thick layer of a conductive material and ferromagnetic. The range itself creates an alternating magnetic field that will be picked by the pan. The pan has a closed path for the currents. The current will establish there, and because of Joule losses, they heat up the pan.
Sir, wouldn't this kind of be acting like a dampener in a mechanical system? Aha,
very good. Exactly. This is indeed very good. This is what it is. It's a damper. It's a pure damper, because so let's put it this in this example here. If we move the plate to the, what is this? This is the right. There will be a force to the left. Right? And this force, as we are going to see later, will be proportional to V. And this proportionality constant is actually the strength of the magnetic field. Now you're going to see that, and this is exactly what a damper is. You see force equals to a constant times the speed. It's a damper. It's a perfect definition of a damper. All right, any other questions?
Well, I just had a quick question about the magnetic flux.
Yep.
So you said that if the area stays constant, the dA just becomes A, but like, I can't think of any examples where the area would be changing. So would you be able to provide one, please?
Let me rephrase that. Instead of saying a constant area, an area that is defined easily. Let's say if your area has a complex shape, you would need to integrate the area in small portions. So let's say this area here, you would need to take this differential area. You take this differential area here, we look at B through that differential area, and you do that through all small differential areas until we get the entire integral. If your differential area is constant, that's what I should have said. If your differential area is constant throughout the surface, then your area is A, right? And then you can take the integral easier. That's what I meant to say, right? But you are right, the area typically is constant. Okay, but it's just it's like any integration goes, right? You look at a small differential elements, you do the operation locally, and then you add everything up. That's what the integral represents. But if these elements are the same, then the calculation is a lot easier. Is that okay?
Yep, thank you.
All right, so let's do one exercise here. In this exercise, we have a Magnetorheological fluid, which is a type of smart material that when subjected to a magnetic field, it becomes solid. So it's a fluid that when subjected to approach a magnet to that fluid, it becomes solid. You have probably seen ferrofluids before, how they are attracted by a magnetic field. This is not different. The only difference is that the particles are bigger. And this solid material, when exposed to a magnetic field, this fluid becomes solid, and you can use that to make brakes, for example. You put the material between two plates that is light with respect to each other, and when you approach a magnetic field, the viscosity changes, so the resistance that is required between the moving plates changes. That's the principle of Magnetorheological brakes. There is a link there at the bottom. You can look at it on the lab website to see how a brake based on this principle works. So here we have set up with that system, with that fluid. And when subjected to a magnetic field, the fluid changes its apparent viscosity to the point it becomes a viscoelastic solid. The required field density to achieve solid state is 0.8 Tesla. If the length of the mean core path shown is 360 millimeters, and the relative permeability of the fluid and core are 4 and 1178 respectively, calculate the required current in the coil. So all this to say that we have to establish a magnetic field through two different materials, and we want this magnetic field density to be 0.8 Tesla at the fluid. So how are we going to do that? Any ideas? So we want the magnetic field to be established in the core, so right here, right there, and you want this to be 0.8 Tesla. What is the current required to achieve 0.8 Tesla here through this material? This is the fluid, but you also need to go through the core that has a different permeability. Or you can think about a electrical circuit. We would need a current to flow through this. The current will establish a potential difference here of some volts. We know the core path, which is given as 0.36 meters. We know this distance here, right? So we know all L's in the calculations. We know the relative permeability of these things. And you want to establish 0.8 Tesla. Now there is a key concept here. Notice that this thing has the same cross-sectional area. It's not said on the paper, but it goes into the light board to a depth that is constant, which means that the cross-sectional area throughout this entire thing is constant, is the same. So in order to establish 0.8 Tesla here, we need to establish a given magnetic flux. The magnetic flux is the same throughout the entire circuit. Like there's someone with the microphone on. If you could turn that off, that will avoid some unwanted communications. We will establish 0.8 Tesla, the same magnetic flux throughout the entire circuit. Because A is constant, then the magnetic flux divided by A is B, is also constant throughout the entire circuit. So in order to establish 0.8 Tesla here, we need to establish 0.8 Tesla everywhere in the circuit. Is that clear? Because if this did not have a constant cross-sectional area, to establish 0.8 Tesla here would be equivalent, would not necessarily establish 0.8 Tesla there, right? Again, the flux, magnetic flux is constant, is the same, because the magnetic, because the cross-sectional area is constant, then the flux divided by A is also constant, and it is the same throughout the entire circuit.
Sir, could you clarify which cross-sectional area you're talking about? Like, which part of this diagram would you be talking about here?
Like that. So if we look at this area here, where the flux goes through, like that, this is A. This is the cross-sectional area.
Okay, thank you.
Right, and this would be our L, like that.
Okay, that helps a lot.
Right?
Thank you.
So you see that A is constant, right? So B is also the same throughout the entire circuit. All right, so let's just start with the core. For the core, we need to establish the entire current. So to establish the current, we need to see what magnetomotive force we need for each material, and then we add them up. We are basically calculating how much voltage we would need to establish a current in the core, how much voltage we need to establish a current in the fluid, and then you just add them up. So let's just start with the core. We know that we have the force, magnetomotive force is the integral of HdL, which in this case can be simply H times L. We know dL well enough. What is H? We don't have H, we have B. And we know that B equals to mu times H. So the magnetomotive force required here would be B over mu times L. Does that make sense? So this is for the core. So this mu here corresponds to the mu from the core of the system. L is the length of the core path that is given, and B is the induction we want to establish. So the magnetomotive force needed in the core, let's call this Fc, is 0.8 divided by the permeability of the core. We have the relative permeability. How much was that? That is 1178. That is mu R. So 1178. So this is again mu R times the permeability of the vacuum, 10 pi 10 to the power of minus 7, 4 pi 10 to the power of minus 7. Right, this is mu 0, and this is mu. And times the core length, which is 0.36 meters. Is it? Yeah, 0.36. And this gives the required magnetomotive force to establish 0.8 Tesla in the core. And that is, if I'm correct, 194.4 amp turns. Now I'll let you think about the fluid. We did this part here, this entire part there, plus this. This is 0.36. This has a relative permeability of 1178. We now need to establish 0.8 Tesla here and here. So I'll let you think about that calculation. How would that one look like? This would be the F fluid. F fluid is the same as B mu L. B is 0.8. Mu is the permeability of the fluid itself, but now we have a different permeability. You see that the relative permeability here is 4. That becomes 4 times 4 pi 10 to the power of -7, the relative permeability of the vacuum. Again, mu 0, mu r, and this is actually mu, times L. Now, what is L? What is L? Any guesses?
Is it 3 millimeters?
Exactly. That's 3 millimeters. So the magnetic flux goes down here, travels there, up and goes up. Right? So goes down here, travels through here, which is already accounted for, right? In this calculation, and goes up through the fluid there. Right? So that's 2 times 1.5 millimeters. Okay, so this gives a induction in the fluid of 671 amp turns. Interesting. Now look at the numbers. We have here 194 to establish a 0.8 Tesla through 360 millimeters. And here we need a lot more, 671 to establish the same magnetic field through 3 millimeters. It takes a lot more energy to develop a magnetic field in a material that has a low permeability, in a non-magnetic material. That makes perfect sense. Now, what is the total induction? That is FC, sorry, now the total magnetomotive force is FC plus FF. And this is actually 671. Here I made a mistake. This answer is actually 477. My explanation still holds, so I just mixed up the numbers here. So please correct that. Sorry about that. And then this plus that is 671. This is the sort of mistakes that you didn't see in control systems because I could just remove them from the video. All right, so this is the total amp turns magnetomotive force needed to establish that flux, that induction. What is the current? How do you find the current now? Any ideas? Well, we know that F equals to Ni. F is given here, 671. What is the number? How many turns we have? 500 is given there, 500 turns times I. This gives a current of 1.34 amps. This is the current required to establish a magnetic flux or a magnetic flux density of 0.8 Tesla. And in this configuration then, the system the fluid would become solid between the plates. Are there any questions?
I have like an understanding question.
Yep.
I'm confused why in this case you're not, okay, I don't know how to word this, but you can achieve a magnetic field of 0.8 Tesla in the whole circuit for much less than you can in that, what is it, the fluid medium, right? So I guess my question is, why are you not, if you just add those two electromotive forces, I think that's what they are. If you just add those two, doesn't that give you a greater magnetic field intensity in both?
No. Because we do need to add them because we have to overcome the resistances of both materials. If we have this only, this does not account for the fluid. If we only look at this permeability, it would mean that this gap here doesn't exist. Everything is connected together, right? If we only look at this part, it means that the core doesn't exist. Somehow we managed to apply the flux only to the fluid. That there's no way to do that. We need to guide the magnetic field. But
Okay.
this part, I think, is the explanation is more clear. If you only apply this, the assumption is that there is nothing in the way. It is only one material. So we do need to account for both of them.
Okay, that makes sense. Thank you.
Oh, all right. So let's move on to exercise number 2. Then I will, as I raise the light board, I will let you read the question and see if you can come up with a strategy to solve it. So here we have a little more complicated system. We have this system with 2 coils. And we want to know the magnetic flux density in that air gap. So the entire structure there has is a material, ferromagnetic material, and there is an air gap that is at distance c. That represents a air gap. The question is, if we apply 10 amps to these coils, what is the induction in the air gap? So the first step to solve this would be to create a equivalent circuit that can be represented like an electrical circuit where the resistances are the reluctance, the flux is the current, and the input voltage is the Ni, the magnetomotive force. All right, so let's do this one. So the first step here, we have 2 coils. These 2 coils are subjected to the same current of 10 amps. So they will establish a magnetic flux. In which way is the magnetic flux created by the first coil? The current is going up, down. So it goes in this direction. Right, it goes clockwise. So the magnetic flux will be pointing down. Can you see that? The current goes counterclockwise. The flux it generates goes down. So the flux here goes like that. This is flux 1. The second coil now has the same. The second coil here, we have a current going up. The current goes clockwise as well, which means that the flux through the coil goes downwards. So now here we have another flux that goes like that and up. It's an assumption. I could have established them differently, but the important thing to see here is that both fluxes going up through this gap. Now we can create a equivalent magnetic electrical circuit. We can start with our input here. The input is Ni. So the Ni for the first coil is 10 times the number of turns. That is 5,000 amp turns. And now where are the resistances in this system? We can now split this into different portions. Let's create one reluctance that goes from this point up to this point. So let's call this point A and B. So we take this entire path, and you're going to call that entire path resistance 1. Or reluctance 1, sorry, reluctance 1. So reluctance 1 here goes from this point up to them, there. What else we have? Now we have this middle section here. This middle section will have 2 reluctances. One is for the gap, so let's call that reluctance A. This is just for the air gap. And the other one is from point B all the way here, and from point A all the way there. So this plus that. The reason I'm splitting it this way is that we have different materials. So for this part here, we need to split that into 2. And let's call this resistance in the center here, reluctance 3. And on the other side, then we have this part, which has the same magnetomotive force in the same direction, and that is 5,000 amp turns. Already. We have two magnetic fluxes. One is going that way. Let's call this flux 1. And you have another one here, flux 2. Now we need to calculate these reluctances. Let's start with reluctance 1. Reluctance 1 is L, let me write the expression here for the reluctance, L times mu times A. L is the path it crosses, mu is the permeability, and A is the cross-section. Where is the cross-section? The cross-section would be the same as before. We can draw that part here. I don't know if you can see. I think I did it too high. It would be something that goes in the board like that and where the magnetic flux goes through. Because the thickness of this wall is B, then the cross-sectional area will be B squared. Is that clear? The cross-sectional area through which the magnetic flux goes is B squared. Is that clear? Yeah?
Can you explain how it's B squared?
I'm sorry?
Can you explain how it's B squared?
How it is?
Yeah.
So
like
let's take
how it's B squared.
Let's put it this way. So here is the cross section for that part there. This is B because this is B, and the problem says that we have a cross sectional area. And the magnetic flux goes through that. So A is B squared.
Sorry, can you explain how you got R1 in the electrical circuit?
Yeah, so R1 is the reluctance from this point all the way to that point. From here to there. All right, and then reluctance A is the air gap, and reluctance 3 is the reluctance from B to this point here. And now that you asked that, I realized that I forgot to add the reluctance here from the other half of the circuit. All right, call this reluctance 2, which is now from this point to point A. All right, so this is one side, and that's the other side. So this side here is represented by R1, and that side there is represented by R2.
Sir.
Yeah.
What's the point of adding R3 if we already have R1 and R4 to compensate for the core material?
Good question. Why do we need R3? Because R1 is only subjected to phi 1, whereas R3 is subjected to phi 1 and phi 2.
Oh, okay.
It makes the analysis easier.
Yeah.
All right. So now let's calculate the core path here. So what is the length from point A to point B? Can you look at the diagram, and what is the total length from A to B?
Is it 2B plus A?
Is it 2B plus A?
I think it's just B plus A.
I think it's just B plus A.
Oh.
Right, because this, I see your confusion. This little portion here is only half of B. Right? Is only half of
right.
This is half of B. Right? And then we have, but we have another half of B here and another half of B there as well. If you take this point as where the loop goes down. Right? So A here plus this part plus that part and plus this 2. So how much is that in total? Is actually 3 times A plus B. 3 times A plus B. Why that? Let's do that again. We have, let me actually do this on the PowerPoint. It will be easier. we have this is the path we want to take. So we have here 1B, right? 1B. Then you have another B. And then you have another B. So 3B plus 1A, 2A, 3A. So 3A plus 3B. Is that okay? 3A plus 3B. Yeah? Let me go back. Silence indicates confusion. So the first blue line there is half of B because you are at the center point. This is another half B. This is another half B. This is another half B. And you also have this one here. So if you only look at the top part there, we have 3 half Bs. And the bottom part, we have another 3 half B. So that is 3B and 3A.
Sir, how do you know that the first B that you indicated in the middle between the two A values, how do you know that distance is B when it's not indicated?
I think it is indicated. I think it is indicated. You have the top B and you have this distance is B. So everything is indicated, I think. All right, but this is simple geometry. We'll see this later. So it's relatively simple. Divided by mu, which is, what is the relative permeability here? Is
1200.
1200 times 4 pi 10 to the power of -7 and times the cross-sectional area, which is B squared. And this gives the permeability of R1, the reluctance of R1 as 2.58 times 10 to the power of 6 amp turn per Weber. We are running out of time, but I'm going to finish this and post it later. So you can stay, but if you have conflict or you are done for today, I will post the final video later. But I will continue this until the end, even though it's already 9:30. This will probably take another 10 minutes to finish. Notice that
Professor,
R1.
I just have a question.
Yeah.
So is B given in the question? I just can't see because you were able to get a numerical answer. So do you know what the actual value of B is?
Yeah, it's given in the question. You see,
oh, okay.
A is 0.5, B is 0.2, and C is 0.05.
Thank you.
Okay. We can also see that R1 and R2 are the same. R2 equals to R1. Right? They are subjected to the same material and the system is symmetric. Now let's do R3. What is R3? We have the same material, 1200 times 4 pi 10 to the power of -7, the same cross section, and that is B squared. And what is now L? What is L?
Is it 1.5B?
It's 1.5B. I think that information might be missing. So we need to do A plus C minus A plus B minus C. That's what it is. A plus B minus C. The distance from here all the way here is A plus B, correct? The distance from here to here is A plus B. Minus C removes the gap. Yeah. You made the assumption that this was B, but this is not given. Actually, this distance was not given.
Yeah,
but you know
that's
that,
yeah.
right? But
Yeah.
you know that from A to B, we have B plus A, or A plus B. Now remove C, and that gives the distance in the path only, in the core path only. So we have everything here. A, B, and C are given. This is 0.82 times 10 to the power of 6 amp turn per Weber. And finally, the reluctance of the air gap. What is that? That is easy. That is C divided by 1, the relative permeability of the air, times 4 pi 10 to the power of -7 times B squared. And this is 9.94 times 10 to the power of 6 amp turn per Weber. All right. So now you have all the permeabilities. All good. Any questions at this point? Okay, I don't think so. So let me erase this and we can do the next step now. You can attempt the next step. This would be this. Now we need to write the equivalent of Kirchhoff's law for this circuit. The equivalent of Kirchhoff's law for this circuit. So take each of these loops that we have here, loop 1 and loop 2, and we can write that that R times phi plus R times phi plus R times phi equals to the input in the very same way that we write Kirchhoff's law for electrical circuits, but now using the analog quantities here in the magnetic circuit. So get to that in 1 second. Let's start with loop number 1. We know that Ni equals to R phi, or phi equals to Ni divided by the reluctance. That is one of the equations we used earlier. And you can now go through this loop and apply this to this entire loop here. So let's start with the loop on the left. We have the input Ni, which is 5,000. This is, let's follow phi 1. What do you have? We have R1 times phi 1 plus R2, RA plus R3 times phi 1 plus phi 2. Does this make sense? We see that here we have 2 magnetic fluxes going up. So we need to add them up. So RA and R3 are both subjected to R phi 1 plus phi 2. Whereas R1 is only subjected to phi 1. So give me the expression now for the other side. For the second loop. This is for this loop. For that loop, what do we get?
Is it the same thing, except the first term is different?
Exactly, it's the first thing, but here we have R2. R2 phi 2 equals to RA plus R3 times phi 1 plus phi 2.
Oh wait, it's equal to, isn't it R2, I2 plus RA, aren't they?
Plus, sorry, yeah, plus. That's plus. All right, so now we can rearrange these expressions. The first one will become 5,000 equals to phi 1 R1 plus R3 plus RA. Just rearrange stuff there. Plus phi 2 R3 plus RA. And the second expression becomes just factoring out phi's here. R2 plus R3 plus RA plus phi 1 R3 plus RA. Right? Just simple manipulation. We didn't do anything other than factoring out R's, phi's, sorry, phi's. Now we can replace the numerical values that we found before. This one here will be 1334 times 10 to the power of 6. And this one here will be 1075 times 10 to the power of 6. And you notice that they are the same actually. Here we have the same value as here, and here have the same value as there. We can now solve for this simple system of two equations. We have two variables. We know everything else is a simple system to solve. And we'll notice that phi1 equals to phi2. Not a surprise because this is symmetric with respect to one another there. And this is going to be 4.134 times 10 to the power of -4. What is the unit for the magnetic flux? That is Weber. Phi1 equals to phi2 equals to, sorry, I made a mistake here. This is actually the sum of them. This is half of that, 2.067 times 10 to the power of -4. Right, a simple system of two equations we solve for. We'll notice that phi1 equals to phi2. It's 2.067. This makes perfect sense because if you look at our diagram here, everything is symmetric. So phi1 and phi2 are the same. All right, so what is now the total induction in the gap? So in the gap, what is the magnetic flux there? Is phi1 plus phi2. And this is where I got that a number earlier, 4.134 times 10 to the power of -4. Right, this value is known, this value is known, and you see that what passes through the air gap is the sum of them, that is 4.134. Any questions at this point? Is there anybody still there?
Yeah, still here.
Yeah, so is this clear? So this is a simple system of two equations. We found phi1, phi2. We know that on the gap, we have the total flux is the sum of them. So 4.134. The question doesn't ask us for the flux. It asks us for the flux density. So what is the flux density in the air gap? What is the flux density in the air gap?
You just divide that by the cross-sectional area?
Precisely, just that divided by the cross-section. So it's phi divided by the area, and the area is b squared. So b air equals to 4.134 times 10 to the power of -4 divided by b squared. Don't forget that this needs to be in meters. So that is going to be 2 millimeters, 0.2 times 0.2 millimeters. That is 4 times 10 to the power of -4. And this gives 1 Tesla. Exactly 1 Tesla. All right, any questions?
I just have one small question.
Yeah.
If you always have a symmetrical diagram, can you expect this kind of analysis every time?
Oh, of course, yeah. You are right. I could have made the assumption here from the first equation that phi1 and phi2 are the same, and then just solve that way.
Mm-hmm.
And it would save us a lot of time. Yeah. So I could have said here, because this is symmetric, then phi1 and phi2 are the same. But I have it here just in case we have systems where symmetry does not apply. For example, if the cross-section on this leg here was different, then this would not apply. All right, so let's do exercise 3. The electromagnet shown can be used to lift a length of steel strip. The coil has 500 turns and can carry a current of 20 amps. The magnetic material has negligible reluctance. This is very important. Let me read that again. The magnetic material has negligible reluctance. It is the same as saying a wire has no resistance. Up to flux densities of 1.4 Tesla. Determine the maximum air gap for which the flux density of 1.4 Tesla can be established. Okay, so you're basically asking that we have a perfect system. The magnetic part here has no reluctance. All we want to do is to determine this gap and maintain a flux of 1.4 Tesla in that gap. So the gap basically is the air, and that's the only part we are concerned with, because the rest is here to guide the flux in a perfect way. The entire structure has no reluctance, which means that it's here simply to guide the magnetic flux through this path. Very well. The question is, what is the maximum air gap that we can have to achieve a induction of, this is a bit off, 1.4 Tesla. So let's call their air gap G. We have a coil here. The coil has 500 turns, and so N equals to 500, and the current is 20 amps. Now this is a common application of the circuits. How would you do that? Then how would you start this? We want to establish a flux of 1.4 Tesla. In this example, because we have straight away the magnetic induction density we need, we don't need to worry about the depth, the area, because you are already given B that we expect the system to develop. We can start this by looking at the integral of a closed loop path of H dl, which is equals to Ni. This is Ampere's law. Let's look at that equation again. Integral over a closed surface of H dl equals to Ni. A closed path, where should we select that a closed path? We can take a closed path from this point to that point, down here. This was supposed to be a straight line, by the way, and up there. This could be our closed path. We could also get the closed path on the other side. That works as well. But let's look at the equation again. Integral of HDL equals to Ni. We cannot select this path. Why? If you take the outer loop here, integral of HDL will be 0, because there's no current going through the surface, through the path. Everything is looping inside there. So we need the current to be flowing in. If our path goes all the way there, then the current flows in and out, and they cancel out, right? So this expression, this little sign here tells us everything. We need the integral over a closed path equals to Ni. The net current that is going in or out. Here, what would be Ni? It would be the number of turns times the current. But if you take this loop, then you have a coil here where the current goes in and out at the same time, and then this should be 0. All right, so this we can rewrite as HL equals to Ni, where L is this path. What is the length of that path? Because we neglected the ferromagnetic material, we said that it has a perfect reluctance. It offers no resistance to the establishment of a magnetic field, and therefore it doesn't need to be taken into account. The only thing we need to cross is 2 times G, one going down, one going up. So now we have H times 2G equals to Ni. And what is H? We have B equals to mu times H. B over mu equals to H. So you can now take this expression and rewrite it as P mu times 2G equals to Ni. B is the magnetic flux density, which is given is 1.4 Tesla. Mu is the permeability of the air gap. G is the gap we want to determine. And Ni is given, is the number of turns in a coil times the current. So now G equals to Ni over 2B times mu. Is that correct? Ni mu divided by 2B. Yep. Yep. Which now gives N is 500, I is 20, mu is 4 times pi times 10 to the power of minus 7. Remember, this is the air gap, right? So the relative permeability is 1 divided by 2 times B, and B is 1.4. This gives the maximum gap for which we can establish 1.4 Tesla of 4.5 millimeters.